Alright students, so in this video we're going to go over the Huckel molecular orbital theory pre-lab activity and reading that you should have already done. If you haven't done that, please stop this video and go back and do it. Alright, so assuming that you all have already tried this yourself, if you had trouble, that's fine. We haven't really talked much about molecular orbitals. Actually, we haven't talked about molecular orbital theory at all yet in class, and that's okay. So this is your first little dose. You may have heard about Huckel molecular orbitals or Huckel molecular orbital theory before in organic chemistry when talking about either the stabilization of resonance. So when you have delocalized electrons, say in benzene, you actually lower your energy or stabilize the molecule. So when talking about that effect, you may have talked about Huckel molecular orbitals. The other place you may have seen them is when thinking about reactivity of certain organic molecules. But regardless of whether or not you remember any of that, we're going to talk about it again. So the very first question asks you which of the 2p orbitals can participate in forming Huckel molecular orbitals. And the answer to that is 2px and 2py, but not 2pz. So why is that? So just a point of convention, we always say that the z-axis is the axis in which bonding occurs. So atoms get closer together along the z-axis to form a bond. And keep in mind that whenever we think about molecular orbitals, the simplest picture of a molecular orbital forming is through overlap of two atomic orbitals on two separate nuclei. So let's draw, we'll start with our 2pz. Let's draw some orbitals and see what they look like. So I've rotated our Cartesian coordinate system so that the z is facing left-right so that we can see that bonding axis more naturally. And so x is pointed up and y is coming out of the page towards you. So we have this 2pz. Remember that red represents negative, blue represents positive. Let's draw another 2pz. We're going to flip it so that the positive ends are pointed towards each other and the negative ends away from one another. So if we have these and they're along the z-axis, remember that we can think about having carbons. The carbon atoms are sitting at the origin of each of those Cartesian coordinate systems. So in between the red and blue lobes, where they come together to form that node, that's where your nucleus is. So if we were to slide these nuclei together along the z-axis, where would our molecular orbital form? So I'm going to smear it with blue highlighter. You've got a molecular orbital that's actually going to form as the overlap of those two positive lobes of the 2pz axis. And this is going to form a sigma molecular orbital. So sigma molecular orbitals they completely encompass the bonding axis or that z-axis. There's no node that breaks the bond or that is parallel and through the bond. There's no nodal plane. So we can break the bond, we can have a node in the middle, and that would cause an anti-bonding, which we'll talk about in class later. But here, this sigma shape, this sigma wraps around the z-axis. And so this is a sigma molecular orbital, not a pi. Remember, sigmas are for single bonds, not for double bonds. So if you have a double bond or a triple bond, then you, in addition to your sigma, then you start having pi bonds, which is what we need. So let's look at the 2px. So we'll erase this, draw another axis. So we have the same Cartesian coordinate. Now the x is pointed up and down. And so we'll draw our 2px with the positive pointed up and the negative pointed down. So the red being negative. And let's draw another one because we need two carbon atoms. So we have our other one. So again, let's imagine that these two nuclei are smooshing closer together along that z-axis. Where's our molecular orbital going to form and what is it going to look like? Just based on overlap of our 2px orbitals. Aha! So if we smear the blue together and smear the red together, you'll notice that there's no molecular orbital touching the z-axis. There's a nodal plane that covers that z-axis and goes between the positive and the negative parts of this wave function. And so here we have a pi molecular orbital because there's no molecular orbital actually touching the z-axis. So this will be a pi type molecular orbital. So 2px is going to give us a pi orbital. Let's try 2py, just for the sake of proving this to ourselves. This one's the hardest to draw, so I saved it for last. Here the y-axis is coming in and out of the plane. So the negative is going behind and the blue is coming out towards you. And let's draw our second carbon atom, same deal. And where will this molecular orbital be? Okay, so now it looks like we took the 2px and we rotated it towards us 90 degrees around the z-axis. So now the blue is coming towards us and the red is going back into the page. But again, there's this nodal plane through the z-axis. The z-axis doesn't have any piece of molecular orbital touching it right now. So this is going to be a pi molecular orbital. And pi molecular orbitals can hold pi type electrons. So the answer to question 1 is that only 2px and 2py can form pi molecular orbitals. So they will be the only 2p orbital types that we consider for Huckel molecular orbital theory, 2px and 2py, because those 2pz's are actually going to contribute to sigma bonds. All right, so the next question was looking at the secular determinant of ethene. So the secular determinant, sometimes it's called the Hamiltonian matrix or other things, but one thing we can call it is it is mathematically a secular determinant of ethene, and it looked kind of weird. So ethene is 2 carbons with a double bond between them, carbon 1 and carbon 2. Your secular determinant should always have the same dimensions as the number of carbons that could have electron delocalization. So here we have 2 carbon atoms that can share electrons, and so we have a 2 by 2, specifically that can share pi electrons. So here we have some interesting terms. These H11s and H22s have they really represent an integral with a Hamiltonian inside. And S11, S12, S22, these are orbitals that are just probability orbitals of wave functions, atomic wave functions. So again, you have a 2 by 2 because you have 2 carbons. The first row and the first column represent carbon 1. The second row, second column represent carbon 2. So let's look at our Huckel assertions that your worksheet talked about. So the first one has to do with this S term, which is also called the overlap integral. So Sij is equal to the wave function complex conjugate of I times the wave function j integrated over all space. So since these are 2p orbitals and they're atomic, they're coming from the atomic wave functions from hydrogen atom, if they match, then we know that they are normalized, and so this integral will equal 1. So if I equals j, this integral s will equal 1. But if this integral will go to 0 if I doesn't match j, because the 2p orbitals from the hydrogen atom are also orthogonal to one another. So S11 and S22, we have the same wave function because it's centered on the same carbon, and so those two will go to 1. They have to be normalized. But S12 and S21, because they're centered on different carbons, are now orthogonal. So this overlap integral will go to 0. So that means we could replace those terms inside our determinant, which we will do soon. The second assertion deals with HII, and we're going to call this alpha. So HII is the integral over all space of the Hamiltonian acting on psi or wave function for I, and then multiplied back by the complex conjugate of the same wave function, integrated over all space. And we know this integral. We've seen this integral before. It always equals the average energy of our system. And so our system here, the average energy that we're thinking about, is the average energy of an atomic 2p orbital, which we're going to call alpha. So we're not going to define it as a number, we're going to keep it sort of in the abstract, but alpha is always the energy of a single atomic 2p orbital. And that means that H11 and H22 both equal alpha. That's another thing that we could replace in our determinant. Number 3 is Hij. So now I and j are different. This is often called the Coulombic or resonance, this is often called the resonance or exchange integral. HII is the Coulombic integral. Hij is often known as the resonance integral, or the exchange. It's the exchange of the electron or sharing of the electron between two different carbon wave functions. So now we've got Hamiltonian acting on wave function I multiplied by the complex conjugate of wave function J integrated over all space. And so this is also going to give us an energy, but not the energy of a single atomic 2p orbital. This is going to give us this resonance or sharing energy of the electron called beta. So let's replace H12 and H21 with beta, which I wrote them both as H12, but we could have obeyed matrix rules and actually used 2-1 some places. I didn't do that, sorry guys. All right, so let's fill in these things that we know back into our original matrix. So along the diagonal in this first term, we have H11, which we know equals alpha, minus E times S11, which we said equals 1. So alpha minus E. And we'll see that along the diagonal, H22 also equals alpha, and S22 also equals 1. So that term will also be alpha minus E. If we look at the cross-diagonal terms or off-diagonal terms, we'll see that H12 equals beta, and S12 equals 0. So we're just going to get beta, or beta minus 0 for both of those terms. And so we can get back the matrix that we were supposed to get. So our simplified, this is often known as the simplified or abbreviated secular determinant or Hamiltonian matrix. So we have that as alpha minus E and beta. And we can use that if we were to solve it, which we won't solve by hand because this is a determinant where all of the terms in the matrix are actually integrals. So we're not going to solve it by hand. That's awful. That would take all day. We are going to let a computer solve this for us every time. If you're really ambitious, feel free, but I'm not going to join you on that journey. All right, so if we were to solve this determinant, we'd get that there are two possibilities, alpha plus beta and alpha minus beta. And for reference, I've drawn in alpha, which is, again, that atomic 2p energy. Alpha is a negative quantity, so is beta. So alpha plus beta is actually going to be the lower energy, and alpha minus beta will be your upper energy. How many pi electrons does ethene have? Hopefully your answer there is 2. If not, we should chat about that. So you have 2 electrons. We're going to put those in, because here we're only thinking about pi electrons. We're not thinking about all the electrons, only the pi electrons. So we have 2 electrons in the pi bond, 2 that are in the sigma bond underneath, which make up the other half of the double bond. All right, so we have 2 pi electrons. We put them in, so our total energy here is 2 times alpha plus beta, or 2 alpha plus 2 beta, because we have 2 electrons at that energy. All right, the next question asks you to look at butadiene's secular determinant. Here we have 4 carbons. Carbon 1 and carbon 2 have a double bond, carbon 2 and 3 have a single bond, and carbon 3 and 4 are double bonded. But remember that 2 and 3 can still experience pi bonding through delocalization or resonance. So if we write this determinant, we're going to see that the diagonal is still this alpha minus E. So alpha minus E is still present, and then if we look at the carbons that are double bonded, they will be beta, just like ethene was. But how about carbons 2 and 3? How do they interact? Well, we said that they have delocalization, so they're also going to be beta. So it turns out that all the carbons that are connected in this delocalized conjugated system will have a beta term in the matrix between those 2 carbons. Because remember, each row represents a carbon and each column represents a column. So you're looking at one carbon interacting with either itself or another carbon. All the other terms, we don't have a bond between carbon 1 and carbon 3, for instance. So we're going to have a 0 whenever we're dealing with carbon 1, carbon 3 interacting, because there's no bond between these atoms. So the rest of our matrix is full of zeros. All right, so we're told that if you solve this determinant, you'll get 4 energy levels. Because there are 4 carbons, you'll get alpha plus minus 1.618 beta and alpha plus minus 0.0618 beta. So we can build an energy diagram just like we did for butadiene. And again, alpha plus 1.618 beta will be the most negative because alpha and beta are both negative. How many pi electrons do we need to put in our energy diagram for butadiene? 4, because there are 4 pi electrons in butadiene. And so we could calculate our total energy by thinking about the fact that we have 2 electrons in the alpha plus 0.618 beta and 2 electrons that are at alpha plus 1.618 beta, and add all of their energies together. and that will go to 4 alpha plus 4.472 beta. Now if we want to think about the delocalization energy, this is the energy difference between the pi electrons, or the pi energy in butadiene, minus that of ethene. So if we look at two ethenes side by side versus butadiene, the difference is there's a single bond connecting the two double bonds in butadiene that's missing in ethene. So there's the ability for delocalization or resonance in ethene or in butadiene that's not present in ethene, or two ethenes stacked next to each other. So the difference then between their energies will give us the delocalization energy, or the energy that we save by having the ability to delocalize. So we're going to go ahead and take our energy for butadiene, subtract 2 times the energy for ethene, so minus 4 alpha minus 4 beta. We'll get 0.472 beta, which remember beta is a negative value, so that means that the energy is lowered by delocalization. So instead of just being 4 alpha minus 4 beta, it's 0.472 beta lower than that, right, in magnitude. And so, again, thinking about delocalization will always save us energy. So we can always calculate how much by calculating the difference between the pi energy of our real system minus how many ethenes could we organize close to each other to give the same number of pi electrons. Okay, in the next video, I'm going to go over how to use the Excel sheet for this lab. Be sure to watch that before you get started.